Hello, welcome to the video lecture series on digital image processing. The term digital image processing, I think, is familiar to many of us because today we are using the digital image processing techniques in several application areas. In this particular course, which will consist of nearly 40 lectures, there we will be covering the basic fundamentals of digital image processing, as well as we will touch upon some specific techniques which will enable us to do some practical image processing which we can do on several application areas. Now, let me first begin with the definition of this subject. I think the title itself suggests its definition. When I say digital image processing, there are a few things which are involved. Firstly, the image that we are talking about is a digital one. That means to say it is not a continuous photograph which we are habituated to see. Rather, it's an image which will be captured by a computer or any other device which will capture the image, and then it will store it in a discrete form. It will convert the image into a digital form, and then the processing will be done in some computational unit. So basically, the term digital image processing refers to the processing of a two-dimensional picture by a digital computer. So that is the basic definition that we can write. It generally refers to the processing of a two-dimensional, because you can well understand that for any picture we will be having two dimensions, that is the x as well as the y. So it's a two-dimensional picture which we have, and if we are digitally processing it, that means to say processing of a two-dimensional picture by a digital computer, this we can give as a definition of this particular subject. But very often many of us tend to confuse between some of the other familiar terms like pattern recognition, computer vision, and many of us have got misconception that whether they are all alike, whether they tend to do the same thing, whether they are the different names for same or a very similar thing. So I think at first I would try to make this doubt very clear in your mind. I mean, I'd first try to clarify the doubts which you may have in your mind. So the doubts are generally about these terms: digital image processing, then many of us have heard of computer graphics, and we also hear about the term pattern recognition. And let me define the goals or objectives of these three subjects. In digital image processing, what we do is we take any image as an input, and then we do some processing on that image. The question is, why are we doing processing? It could be that we are trying to improve upon some specific features of the image, or it may be that our intention is to extract some specific features. We are not interested about the entire image contents, or we are not interested with the details of the image, but we are only interested in extracting something meaningful, something very meaningful, something which are features of the image we can try to extract. So input is an image, some processing is being done, and the output is going to be yet another image. So in digital image processing, what we have is there is a processor which will do the processing. The input is an image and the output is another image which we call as processed image. In case of computer graphics, what we do is we generate some pictures, all right? We generate some lines, we can do some shadings on the object, we can do a lot of other things, and there what we do to the computer, we feed a set of descriptions. We specify that what are the descriptions of the object which we are trying to draw. And then on that object, okay, we do some computer processing so that we can represent that object pictorially or in a graphical form. So in the case of computer graphics, what we have is the input is a set of descriptions. The input is a set of descriptions and we do some processing within the computer, and then the output which we generate is an image. But this image is something which is synthetically generated, in the sense that it is not a real image, not in a real picture, but something which is generated out of the descriptions which we have fed. In pattern recognition, what we do is that we feed an image as an input, okay, and we are interested in extracting some meaningful descriptions out of the picture. Maybe that it is a satellite image and we would like to know that how many different classes are there in the image. It's a remote sensing image and we are interested in identifying that which is the vegetation area, which is the water body area, okay, which are the forests area. Like this, we would like to identify each and every partition. And what we expect from the computer is, we will feed the satellite image to the computer will do all the processing and it will generate a set of descriptions, okay, indicating the different classifications, that yes, you have region number 1 so and so, region number 2 so and so, region number 1 having this much of area, like a set of descriptions are generated out of the image, okay. That is a pattern recognition, sometimes we call it as pattern classification. So these are the different objectives of these three subjects: digital image processing, graphics, pattern recognition. We also hear about yet another term which is called as computer vision. And in case of computer vision, what we really have is the computer vision must be preceded by some digital image processing operation. Means, given a raw image, we will generate a processed image, okay, by applying any digital image processing technique, and we will try to understand that processed image, okay, and by understanding we will be generating a number of properties, okay, from that given image and have some meaningful information extracted. We will try to recognize the different objects, okay, we will try to give descriptions to these different objects, properties, everything we will associate, and that will be the goal of the computer vision. So we very often hear of all these terms, but our discussions, okay, in the next 40 lectures will be restricted to the subject of digital image processing. All right. Now, you may think that the subject of digital image processing is very new, because you might be hearing about the term digital image processing quite recently. Maybe for the last 10-15 years you might have heard about this term. But let me go back to the history. I think you'll be quite surprised to know that even as early as in 1920, okay, people had used image processing techniques. Okay, you know where? That time people were sending newspaper pictures from London to New York by submarine cables. Okay, so they required transmission of pictures, meaning that they also had to look for the quality of pictures which are being sent, okay? And that was as early as 1920, when we did not have all the computers that we have today, okay, nothing of this kind. Then say around 30 or 32 years back, when people were conducting the lunar missions, okay, at that time we all remember that we used to see the pictures which used to be sent from the moon, okay, and sometimes pictures were also collected from other planets and we could see them, okay. So at that time also some image processing techniques were being utilized, okay. But there were a lot of problems about image processing in those days, and as I told you that we did not have any sophisticated computer which we have today. And image processing, digital image processing, is something which is generally a very, very time consuming process, okay, because what you have to really do is you have to subdivide a given image into a number of small picture elements, and those small picture elements we call as pixels. Let us look at any typical image. Supposing somebody gives me an image like this. Somebody gives me an image like this, okay, and I would like to put this image into the computer. What I will be really doing is, this entire image I will be dividing into a small number of picture elements, very small number of picture elements, okay, and then to each such picture element I will associate a number. And what is that number? You can clearly see that. Why are we able to make out that which person is there in this image, or what is the background and all these things? How are we able to make out? Very clearly there are intensity differences, okay, which are existing in the image. You can see that this part of the face, okay, is a little brighter, the hair is quite black, okay. This is the background whose brightness will be in between the hair and the brightness regions which we find in the face, okay. So every region is having its different intensity, and we can identify that which region is, I mean we can find out that there are intensity variations. So what we will be doing is, we will convert this entire image into a two-dimensional array of picture elements. Picture elements, which we will be calling in short form as pixels, or very often we call them as pels, P-E-L, pale. Now all these picture elements we have to store in a digital computer. Now see that this, I mean in order to store this picture effectively, okay, the question is that how many such pixels do we take along the x direction, how many picture elements do we take along the y directions? If I take a very small number of pixels, then naturally the pixel size will be bigger. If I ask you that you take only 16 pixels from here and 16 pixels from here, what you will see really out of this image is a very coarse image, okay, because there will be 16 pixels along x, 16 pixels along y, totally there will be an array of 16 by 16, that is 256 elements. So there the resolution of the image is very important, okay. Now it is seen that generally a picture of this kind, in order to represent the picture effectively, okay, with a good amount of resolution, we go in for an image size which is typically of the order of 256 by 256 pixels, or very often we go in for even higher size of image, okay, or higher resolution, having 512 by 512 pixels. What happens in the process is that if you are having any picture of a size like this, okay, say 512 by 512, you can really see that in that case every picture element will be a very small element, and you can represent the intensity value in that particular small area. Next, what we do, that we form an array of these numbers, let us say 256 by 256, and in every such picture element we will be giving a numerical value, and that numerical value corresponds to the intensity level of the image. Again, the intensity is something which is supposed to vary continuously from very dark to very bright, all the way it can vary, and our computer certainly cannot accommodate, okay, all the different gradations which could be present in the intensity. So even the intensity also must be discretized. That means to say, it must be restricted to only a set of levels. Okay, if I have the intensity variations, okay, all the way from this range, if this is the minimum intensity and if this is the maximum intensity, okay, what we will simply do is that we will divide this intensity into a large number of steps. Again, the step size is very much important. If I make the step size too small, okay, then I will be needing a large number of gray levels, a large number of intensity levels. If I make the step size too large, in that case I will be needing only a few intensity levels, no doubt, but my image will look very, very coarse. So it is also found again, okay, that for an image of this quality, okay, which we normally deal with, we require at least 256 intensity levels. If you have more than 256 intensity levels, it is good. Okay, say you argue with me that instead of 256 intensity levels, we will be using 65,536 intensity levels. Well and fine, your picture will look better, but only thing is that whenever you are storing the image in a computer, if it is 256 intensity level, you can store every pixel, okay, in 1 byte. 1 byte corresponds to 8 bit, so it can cater for 256 intensity levels. But if you are wanting 65,536 levels, 64K intensity levels, then you require 16 bits or 2 bytes for every pixel. Well, if you have that much of memory within a computer, you can do that, but it is found that generally 256 intensity levels is quite sufficient, okay, at least as far as the eyes are concerned, because ultimately our eyes are going to be the detector. Okay, so if our eyes can detect 256 intensity levels, okay, very easily, why not going for that? So the requirement that we have is that given a digital image, we have to break it up into a large number of pixels, maybe 256 by 256, 512 by 512, these are some of the typical orders, and we have to divide the intensity again into some discrete levels. It is found by experiments that 256 intensity levels are quite sufficient for eyes, so we have to now represent this picture in a computer. And then it could be that our objective is to extract some meaningful information out of this image. Let us say somebody is interested not about the entire image, but somebody is only interested about the prominent outlines of the image, or rather the places where there is a prominent change in the intensity. Okay, you can see in this image that a human face is there. Okay, the face is having some outline, and obviously that outline is having some, that outline is specifying some difference of intensity between this region and this region. There are one or two objects which are present in the background. There is yet another object, I think a window is there in the background. So we would like to extract the outlines, or rather the places where there is a discontinuity in the intensity values. So we would like to do some processing with this image, and we would like to generate an image of this nature, where I can very clearly see the outlines which are present in the image. So you can see here that I can make out the outline of the face, I can make out the outline of the person's eyes. Then even some of the background objects also I can make out. Okay, here you can see some outlines of objects are there. I can make out where the window is. Okay, so this is a processing. I got this as the input image and I got this as the output image. So this process is the edge extraction process, but all the time I may not be interested in edge extraction. My objective may be to improve the quality of the image. It could be that the image is of a very poor contrast. Okay, supposing if I had got an image like this, supposing I have an image of this nature, what you see on the left. This is an image which is having a very poor contrast. Okay, and we may like to improve upon the contrast and try to get an image of this nature. All right, so this is also a part of processing. So this will be the input image, this will be the output image. Now it is not that every time we do image processing we improve everything about the image. That is not possible. What we can attempt to do only is improve certain features of the image, maybe only the contrast, maybe enhancing the details, the outlines. Okay, all these things we do. So there are several such image processing or digital image processing techniques which are available, and in the next 40 lectures we are going to learn about all of them. All right. Okay, as I was telling you about the history of image processing. So I told that we had it in 20s, we had it in the 60s, but definitely at that time image processing wasn't very popular. Okay, people used image processing, but only in places where you used to find big computers, there you could apply the image processing techniques. But as the computer technology as the computer technology improved in leaps and bounds, okay, from 70s to 80s, every year we are having faster and faster computers available with us. So the problems which were there previously, okay, meaning that the large amount of computation time and the requirements of very large mainframe computers, okay, they were no longer valid, because you have such a high powerful computers, okay, right at your desk. Today you have very high powerful computers available. Okay, you have the personal computers, you have very fast workstations available with you, and today you can do image processing, okay, right at your desk. You do not have to go to any general purpose computing facility to have that. And wherever you need any special processing, even the special purpose hardwares are also being built. All right. So today, or rather I should say that as the computer cost kept on reducing, as its computational power kept on increasing, okay, the use of image processing, okay, massively engulfed, okay, all the different application areas, okay, and I'll be talking about what major application areas do we have with image processing. But let me tell you one thing, however best attempt I may make, okay, my list will not be exhaustive, all right, because I think if you ask me the question, tell me where I can use digital image processing, my answer will be, you name it, meaning that you can use in varieties of applications. But let me tell you some of the prominent applications where image processing already had a success. All right. So the different applications with which we use are, The first, so these are the applications. And the first prominent application, as I was telling you a little while back, processing of remote sensing pictures. And there are varieties of uses for this: tracking of earth resources, geographical mapping, prediction of agricultural crops, prediction of urban growth, weather predictions, flood control, and lot of other environmental monitorings, okay, can be done by having a suitable remote sensing picture processing, okay. And today the entire remote sensing communities, okay, in India as well as in abroad, okay, they are extensively making use of remote sensing picture processing, okay. Then another major application area is in image transfers, image transmissions rather, and storage. There are a large number of requirements where you'd like to transmit your pictures from one place to the other. And the problem that you normally face is, if you are trying to transmit an entire picture from one place to the other, you remember I was telling you that a small picture like that, the one which I showed you sometimes back, may require 256 by 256 pixels, each pixel containing 8 bits or a byte of information. So that means to say that entire picture was having 64 kilobytes. And supposing I am going to transmit a picture in real time, or a sequence of pictures I am going to transmit in real time from one place to the other. So that means to say what? That in 1/30th of a second, okay, I am getting one frame, okay, and for every 1/30th of a second, mind you, I am getting an image of 256 by 256, those many number of bytes. So that means to say 64 kilobytes of pixels I have to transmit for every 1/30th of a second. You can well imagine that what a difficult task it is, that if you are calculating the bandwidth, okay, of the channel that can transmit this image, you will find that the bandwidth requirement is enormous. So it may not be possible for us to transmit the entire image of 256 by 256 by 8 pixels. What we would like to do is to apply some suitable image compression technique, okay. Image compression technique means, if it is possible for me to represent the same image in a less amount of space, okay, as far as the computer storage is concerned, okay. You see this image, you will find that there could be a number of redundancies, okay. An image like this will contain a number of redundancies. I tell you what type of redundancies you normally find. You find that there is invariably a relationship between the intensity of the pixel with the intensity of its neighbor. You can see that if any particular pixel over here is of high intensity, all its neighbors also tend to be of higher intensity, okay, of a very similar intensity. Similarly, take the region of the hair. There, pick up any pixel, it is black, its neighboring pixels are also black. Of course, that neighborhood thing will not hold good whenever we are talking of the regions of intensity discontinuities, but apart from that, any smooth image intensity region will be having similar neighborhood property. Like this, there are redundancies which are present in the image, and if I can make use of those redundancies, then it is well possible that I can represent the same image in a lesser space, okay, in a lesser number of bytes. So the technique of image compression is there, okay, which we have to utilize for transmission of digital image. And in today's context, it is very much necessary because today you are finding plenty of applications with the multimedia. Okay, in multimedia communication, we are transmitting image, speech, videos, animation, everything we are sending through the communication channels, and there we have to evolve very effective techniques of image compression, and this is where image processing comes into picture. Another area, okay, which is a very developed area, is in the field of medicines, that is in the medical image processing, or rather I write it as the medical applications, processing of X-ray images, ultrasonograph images, or the projection images of computer-aided tomography. All these things, okay, are possible today using image processing, and today doctors, I tell you, doctors are using these kind of image processing techniques, okay, very effectively for diagnosing the diseases. Okay, they can compare a normal image with an abnormal image, okay, in order to detect the particular disease, or they can detect that whether after undergoing some treatment, okay, a person is really showing some signs of improvements, again by comparing the person's previous image with the present image. Then another application, very useful application, is in military. Okay, and there also people are using the image processing techniques for a long time, okay, where they have to detect, recognize and track a large number of targets, okay, or if they are going to do guidance or maneuvering of some aircrafts or missiles, there also digital image processing techniques can be used. All right, large number of applications are there today. And then another application is in the industrial machine vision. Industrial machine vision. And in that, what we normally do is that we can inspect objects by applying digital image processing techniques. Supposing some industry, they have manufactured some object of this nature. Supposing this is an object that they have made, and we may be interested in finding out its dimensions, okay, we may be interested in finding out its surface finish, okay, and several other visual properties of this object we may like to find out. Now very often we do it, or rather we are accustomed to do this kind of inspections using human inspectors. Okay, so if a factory is producing thousands of pieces every day, an inspector will be there, or several inspectors will be there, who will be sitting and who will be inspecting each and every item, okay, and then they will take a decision whether to put it in the acceptance bin or whether to put it in the reject lot. Okay, they will be doing this kind of a thing, okay, all over the day they will be doing, and it's a very tedious job. And not only that, there are number of times there are subjective decisions which come into picture. He may think sometimes that, look, I find that the surface finish of this object is okay and I accept it, and at some other time another object comes with a very similar surface finish, but maybe this time I just say that I think it's not good, I just reject it. So this kind of decision makings are very often there, especially when we are doing visual inspection, where it is, wherever it is parametric, it's well and fine, where we can specify a parameter that, okay, like say for example in the case of dimension, it is specified that if the dimension is this much plus or minus this much, you accept it, otherwise you reject it. But wherever there are subjective decisions, whether the surface finish is good or the surface finish is bad and something like that, there, okay, the digital computer can help. It can capture the picture and it can analyze the texture of that image and study its surface properties, and then it can find out some specific parameters out of those surface properties and then take a decision that whether to accept it or reject it. And not only that, the the visual inspection using human inspectors, they generally tend to be quite slow, in the sense that many a times whenever an industry is producing a large number of objects every day, we do sample inspections, okay? Whereas a real-time processing, okay, or rather a real-time inspection is possible by using the industrial machine vision techniques, where image processing really helps us to do that. Some of the other applications are automated assembly. Like say for example, a robot is there, okay, which is assembling some items, okay, and the idea is that the robot must automatically pick up the items and help in the assembly. Like say for example, in a particular bin, okay, in a particular tray, we have some objects like this. Supposing we have these different objects, okay, on a tray, and a robot is there, okay, to help us. A robot will pick up, the robot will be having all the assembly instructions. It will be having a camera with him, okay, and that camera will capture this picture, and then some processing will be done to make out that which is this object, which is this object, which is this object. So the computer must be able to process this image and identify that which part is the screwdriver, which part is the hammer, which part is the spanner, like that. And supposing at some assembly stage I am required to pick up the spanner. So what the robot will do is that it will capture the image, the processor will tell him that this is the coordinate of the spanner, okay. The processor identifies the spanner, and then it tells the robot that this is the coordinate where you can find the spanner, and the robot arm will come and it will grip this piece and use it for assembly. So you can use the digital image processing techniques for not only for machine vision, rather for automated visual inspection, something which I was telling you sometimes back, but also for automated assembling using robots. These are, as I told you, that these are just some of the uses. Another use I can think of is document image processing, okay, where supposing I'd like to recognize a set of handwritten characters, okay. I've got some handwritten documents and I'd like to recognize each and every letters, okay, and I'd like to compose the different words with their meanings, and I'd like to process either a handwritten document or maybe a textual document. My objective may be to extract some drawings, to digitize some drawings, or to extract the different dimensions which are present in an engineering drawing automatically from an image, okay. So again, there we have to apply the digital image processing techniques. And as I told you, if you ask me which application should I use image processing, my answer will be you name it. Wherever you have images, okay, doesn't matter what type of sensor you are using, okay, doesn't matter whether you are using infrared sensor, doesn't matter whether you are using other sensors, okay, you can, as long as you can do some kind of an imaging, okay, you can also do digital image processing. Now let me just show you the typical block diagram of an image processing system. An image processing system will be having this major blocks, okay. There will be a camera and a digitizer, okay, and the camera, this is a camera, and I have some image over here, okay, and from the camera and the digitizer, the image will be taken to an image processor, and then the image processor will be linked to a digital computer, okay, Now don't get confused. Many times we combine these two blocks together, okay? Means wherever we do software digital image processing, what we do is we do the processing within the digital computer itself, okay? So these two together becomes one block, but very often we may also like to have a special purpose pre-processing hardware, okay? And that's how I have separately maintained this block of image processor. Along with digital image, with the digital computer, we need to have mass storage. With the digital computer, in order to communicate with the digital computer, we must have an operator's console with display and the keyboard and maybe other devices like mouse, tracker ball and all such things. And the image processor will give its output to a display, okay? And if we like, we can attach some hard copy device also. So this is how a typical digital image processing system looks like. So this is a block diagram that I have shown. So from the physical world, from the physical image, okay, camera digitizer, image processor, digital computer, then giving the processed image to the display, and then if you want, you can have a hard copy device, okay, to get this, okay. Hard copy device, most of us today use the high resolution laser printers. I think high resolution laser printers gives us quite a good output. In fact, the image which you are seeing from here, okay, this was an image which was generated in our computer vision laboratory at the Electronics and Electrical Communication Engineering Department of IIT Kharagpur. Okay, there this image was generated, and what you see is a laser printed image. So these are, but if somebody goes in for a costly hard copy device, okay, one can get maybe a photographic quality images. Now let me tell you about the coverage which we are intending to have in this digital image processing course. So I talk about the course coverage. Now we will begin our series of lectures, okay, with image fundamentals. In this, we will be basically defining some of the relationships between various pixels, okay, and we will show you how to represent an image, okay, and what are the basic relationships. All these we will cover under image fundamentals, and after that we will be going over to imaging geometry. So our topic number 2 will be imaging geometry, okay, where we will be talking about the where we will show that how actually the images are formed, okay, from a physical world into the camera coordinates, the transformations which are involved in the process, okay, the perspective projection, the orthographic projections. These are the things which we will be discussing under the imaging geometry and projections, okay. We will also cover, within this imaging geometry, we will also cover stereo images, okay. Let me tell you, or rather stereo imaging part we will cover. Let me tell you that stereo image also is a very important thing in image processing, because if we see an image like this, what happens to it is that the depth information that is present in this image is lost, okay. I don't know that whether this person, okay, is, with respect to camera, whether this person is, at what distance this person is sitting, at what distance these walls are there, at what distance these backgrounds are there. I can't make out anything from here. Okay, all that I have is a set of intensity values on an xy plane. That's all. I do not have the depth information, okay, or the distance from the camera to the actual object point. That information is missing. If I have to retrieve that information, then instead of using a single view, we have to go in for two views of a picture. Okay. So what we are going to do is, we are going to take two images, okay, of the same scene but from two different positions. And then what we are going to do, we are going to compare these two images, okay, and then we are going to find out the relative shifts of different objects. And the relative shifts, like you may find that this particular object has been shifted more, maybe in comparison to some other object. Maybe as compared to this object, the shift for this one is different. So like that, we are going to measure the shift, or what is known as the disparity, okay, and then by comparing the, I would call this as the left view, okay, and I would call this as the right view. By comparing the left view and the right view, we will be able to determine the depth, we will be able to extract the depth information, okay, if the imaging geometry is well known to us. All right. So that is what we will be attempting under the coverage of stereo imaging, although we will be discussing about the imaging, not about the matching part. That is to say that how to do the correspondence between the left image and the right image we will not cover, but the stereo imaging principles. So I can say stereo imaging principles will be covered under this part of the course. Okay. Then our topic number 3 is image transformations. So here what we will study is how to transform an image from a spatial domain into some other domain where we can conveniently represent the image. And usually the objective which we have in mind is that whether we can, if we can transform the image from the spatial domain to any other domain, okay, whether we can compress the image properly, or we can extract some meaningful features which we may not be able to locate otherwise within an image. So this will be our next topic of discussion. Then we shall also cover image enhancement and filtering. That means to say, given a poor contrast image, okay, how to improve its contrast, how to do the enhancement, or doing a low pass filtering, a high pass filtering, or band pass filtering, this type of filtering on the images. Just like the way you can do low pass filtering, high pass filtering, or band pass filtering on one dimensional signals, okay, doing the filtering on images is a very similar principle. All that you have here is, instead of a one dimensional signal, you will be having two dimensional signals on which you will be doing this type of operations. The fifth topic under our coverage will be image restoration. It is something like this, that if we have, okay, an image, okay, which is degraded in the sense that if the quality of the image is affected due to some process, it could be that we are taking the image of a moving vehicle. Now what happens is that we are having a camera, and the camera aperture is open for a finite duration, and within that duration during which the camera aperture is open, a moving vehicle has moved by some distance. So in effect what you see in the image is a blurred image. Okay. Now this is one of them. Many times you take many astronomical pictures which are affected by some degradation process. Now whatever it may be, the thing is, if the degradation process is known to us, if we know very clearly that why it got degraded, or if there is a mathematical model, okay, which tells us that how an image has got degraded, okay, then it is possible for us to restore the, I mean, given the degraded image, we can restore what our original image would have looked like. Okay, so that means to say, if some model is there, okay, that means to say this is the original image, okay, that means to say what the image should have been, it got degraded here in this block, and then this is the image what we see, okay, this is the image what comes to us, or rather I call it as degraded image. And if I just have a transfer function h for this particular block, okay, and if somebody gives me the degraded image, okay, and if I have got an idea of this transfer function h, okay, all that I can do is to have an inverse of this transfer function, okay, and try to restore the original image. And this is what we will be attempting under the subject of image restoration. Mind you, there our degradation model must be very well known. The next topic to be covered is image segmentation. That means to say, given an image, how can we break the image into different regions, different regions of different intensities, okay. Like say for example, if somebody gives me this image, okay, I can say that this is one region, this is a second region, this could be a third region. Like this I can break up, the background is yet another region. Like this I can break it up into several segments depending upon the similarity property of pixels. All these things we will be studying under segmentation, and along with that, along with segmentation, we will also study how do we represent the segmentation as the segmented image, that is to say the problem of representation. And towards the end, okay, we will be also discussing about the image morphology, okay, which today has become a very effective technique, a very effective as well as extremely simple technique, okay, whereby we can extract the features, okay, without doing any complicated numerical conclusion, without doing any complicated numerical computations, okay, we can just do some very simple Boolean operations or set operations we can do, okay, in order to extract specific features of the image, okay, and the subject of image morphology also we will be covering. Now, just to tell you about the different reference books, okay, which we may use from time to time, okay, let me suggest some books. The first book that I can refer to you is the book by, so these are the reference books. The first book is by A.K. Jain. The title of the book is Fundamentals of Digital Image Processing. Okay, the book is published by Prentice Hall of India, so it is available in a cheap edition, Prentice Hall of India, and it is published very recently, that's to say in the year 1995. The second book which I can prescribe for you is that by R.C. Gonzalez and Woods. The book is named as Digital Image Processing. and this happens to be an Addison Wesley publication. Addison Wesley. Actually, this book is an extension of, there was an earlier book by Gonzalez. In fact, there, his co-author was Gonzalez and Vince. I mean, that book was by Gonzalez and Vince, and the book has been thoroughly upgraded now, okay, and it is now co-authored with Woods, and the name, of course, continues to be Digital Image Processing, okay, but this is a more recent book, okay. And then another very important book is by Rosenfeld, A. Rosenfeld, okay, and A.C. Koch. And the name of that book is Digital Image Processing and these appear in 2 volumes, volume 1 and 2, okay, and this happens to be an academic press publication. Okay. Apart from that, I can also suggest the book by W.K. Pratt. Okay. The name of that book is Digital Image Processing. And this is a really InterScience publication. Well, the book was published first in 1978, but nevertheless, I think as far as the image fundamentals are concerned, this book is still very nice, okay? I mean, as far as the fundamental treatment is concerned. So even though it is 1978, don't think that the book is absolutely backdated. It may not contain the recent developments, but at least the fundamentals are existing. So I think the rest of the topics, I mean, we will begin with the actual lecture series, okay, from the next one. Let's say with the image fundamentals, we will start our lecture process. I mean, this is just to give you an introduction of the subject, okay. Thank you.